All right. So this general body meeting is going to be on Intro to Reverse Engineering, and John's going to go ahead and present. Before we do that, if you want to be part of the mentorship program, please fill out this form by Friday at midnight. We are going to be closing it off for mentees by that time. Mentors, if you're wanting to be a mentor, you can reach out to me after that deadline, but there's no guarantee you will be matched with a mentee. Unfortunately, we do have to cut it off for mentees at a certain date. Otherwise, we can't guarantee matches. So mainly this is an opportunity to help all of you grow your skills, either by teaching it to someone else or by having it presented to you. It's also an opportunity to get involved further in the club and have some fun with additional events that we host for the mentorship program. So we're going to be organizing via Discord. So when you fill out that form, please add your Discord handle. And then if you applied in the fall semester for the mentorship program, but you haven't already been added to the mentorship chat, please send me your Discord handle so I can add you. That pretty much covers all of our announcements. So I'm going to go ahead and turn it over to John. And then John, you should have the ability to screen share.
It's oh, you're still sharing, so I can't.
Yeah. There you go.
All right, everyone able to see? Someone confirm. Yeah. Are you guys able to see the right screen?
We can see it.
Okay. All right. Well, I'm going to go ahead and get started because there's kind of a lot to cover, but we're going to go over Intro to x86 Reverse Engineering. You're probably going to want to know about C or another low-level language, binary and hex, general computer proficiency. If you want to follow along, you're going to need a Linux virtual machine or WSL if you're on Windows, and Ghidra. So if you don't already have those, you want to follow along, you have time to install them now, but I'm not going to walk through it. So kind of an overview of what to expect. I'm just going to go over a high-level overview of reverse engineering and a quick crash course on x86 assembly. We're going to go over some common reverse engineering tools and do some guided walkthroughs of challenges. I do have the chat on the other screen, so if you have questions as I'm going, feel free to throw them in the chat and I or somebody else will answer them. I'm going to grab some water real quick. So this is just going to be an intro talk. I have kind of intentionally simplified some of these topics because frankly, you could have a whole presentation on each one of these slides. So if you're a little more familiar with reverse engineering, some of this might sound off to you, but I'm trying to just keep it simple so it's easy to get started. So if I can get a quick poll, how familiar are you guys with reverse engineering? Because that will kind of give me an idea of how to pace the presentation. So if you just drop like a number on this scale in the chat, so I have an idea of kind of how fast to move, how much to explain. All right, so I'm seeing a lot of, 1, 2, a couple of 3s. So I think that's probably good. It's good that you guys are here. Owen's definitely a 5. Don't be humble. All right, so let's get started. So reverse engineering is basically software analysis without source code. So since you don't have source code, you're going to be using other tools like disassemblers or debuggers to get the information you need. And your ultimate goal is to discover how a piece of software works. Why you would want to do this is a good question. If you're familiar with jailbreaking, every jailbreak you ever had on a phone required some sort of vulnerability that somebody had to discover through reverse engineering. If you want to analyze malware or ransomware to learn how they work, you need to be able to reverse engineer. Maybe there's a piece of software you use that's no longer updated and you want to make a clone. Well, you could reverse engineer it to find out what it does and then make your own version of that software. Creating game cheats or mods definitely requires reverse engineering, and obviously bypassing software copy protection, you can also do with reverse engineering. I'm going to get right into processors and assembly, which are kind of two of the main things you'll need to know about. So I'm sure everyone knows processor is kind of the brain of the computer. It executes a series of instructions. If you're not familiar with instructions, you can think of them as primitive operations. Basic arithmetic, copying data from one place to another, stuff like that. Nothing advanced. It's all broken down into simple steps. When you have a program on your computer, those instructions are encoded as bytes, and that's what the processor executes. That's called machine code. When you're reverse engineering a program, you're going to be looking at assembly, which is just a written textual form of that machine code that you can read as a human. You might have seen x86 in the presentation title. x86 refers to the processor architecture. So if you're watching this on a laptop or a desktop, it's almost certain that your computer uses the x86 architecture. There are other architectures, different processors use different things. I'm going to be talking about x86 today. Quick refresher on data units. So a bit is like the smallest unit of memory or data you can have. It's equivalent to an atom. Byte is 8 bits. A word is 2 bytes. Double word is 2 words. It's kind of a chart below if you want to see. You might also see a quad word, which is 4 words. Pretty self-explanatory. So built right into the processor, and pretty important part of reverse engineering is what's called registers. They're these small, fast data storage units, and they're built right into the processor. They're essentially a variable, so you'll see them referenced when you're reading assembly, and you can think of them like a variable. There's only 8 general purpose registers in x86, and they're all 32 bits in size. These are those 8 registers. So you can see they all have names that kind of follow a pattern: EAX, EBX, ECX, EDX, so on. For the ones in blue, you don't really need to know a description of them. I have them there if you're curious. The ones in purple at the bottom, though, you should know what those letters stand for. There's the stack base pointer and the stack pointer. Those will become more important as we get further into the talk. And once again, these are all 32 bits in size. So sometimes you might see these written like this. This is another way of referencing registers if you only want to access the lower 16 bits. There's also like this, where you have AH, AL, BH, BL. This refers to the lowest 8 bits and the 8 bits above that. So Ben brings up a good point. Different processors have different numbers of registers. That's different architectures going to have different numbers of registers. For x86 today, we're only going to deal with these 8. And there are more registers than these that are used for different things, but that's a little bit outside of the scope for today. One of those that is important, though, is EIP, which is the instruction pointer. It's not a register that you can write to like the general purpose ones, and it's managed by the processor. And basically, EIP always points to the instruction that's being executed. So when your program gets loaded into memory, when you run software, EIP is going to point to the instruction that's being executed at that time. So in reality, this is moving around, thousands of times, if not more, a second. But it's basically kind of just like the head on a video player or something that points to where you're at. So this is what some basic assembly syntax looks like. This is a pretty basic line. It's INC EAX. They kind of color coded it so you see what's what. So INC is our instruction and EAX is our register. Most lines of assembly will look something like this: an instruction, and 1 or more arguments. There are some that have none, but the INC instruction increments the value in a register. So this is kind of equivalent to EAX in C or something. Whatever was in EAX is now going to have 1 added to it. So if EAX was 1 before, now EAX is 2 after this line executes. Another super common instruction that you'll see is the move instruction. So in this example, we're doing move EAX hex 12. And that's just like setting EAX to hex 12. If you see, I'll always put the C equivalent where possible below. And most instructions are going to take 2 arguments like this. So in this instance, EAX is copied, or hex 12 is copied into EAX, where EAX is our register, and hex 12, we just have an immediate value in the code. One important thing to note is that this is Intel syntax. In Intel syntax, the destination comes before the source. There is something called AT&T syntax, which is less popular. You're probably going to see Intel in all of your tools. But if you look up online and you see something different, make sure you're looking at the right thing. Otherwise, this presentation won't make sense. Move can also accept 2 registers as arguments. So on the last slide, we were putting hex 12 into EAX. This move line here is putting EBX into EAX. And it's just copying the data from EBX to EAX. Most instructions are able to accept registers, immediate values, or memory addresses as arguments. So there's not, like a strict rule. You can see move instructions with a bunch of different combination of arguments. So as a quick exercise, we just covered 2 of these instructions. Based on what we just went over, I put in the chat what you think after these 5 lines execute. What do you think the final values of EAX and EBX are? Guess we only have 1 taker. Thank you, Mateo. It is 3 and 7. Or no, we have more people now. But yeah, so EAX is going to be 3 and EBX is going to be 7. So we just went over 2 instructions there. I'm going to quickly go over some other basic instructions. You don't have to commit these to memory right now. Most of them are named pretty similar to what they do. But these are just things that you're likely to see when you're doing some of the challenges we might go over later, or just any reverse engineering on your own. The add instruction, there's add, sub, mul for multiply, and div for divide. All do exactly what they sound like they do. So I have those kind of written below in assembly. And then, excuse me, on the right after the semicolon, I have the C equivalent. So in assembly, a semicolon is a comment, if you're wondering. But these are pretty self-explanatory. You also have your bitwise instructions. So these just do bitwise operations. Once again, I have the C equivalent on the right, and you can see the assembly in the C. It's not worth spending a lot of time on these. They all do what they sound like, and you're not going to see these as much as some of the others. Except for XOR, you'll see that sometimes, but data instructions, we already kind of went over. Move, it copies a value from one place to another. It's called move. It should really be called copy because the source is always left intact. So if you see on the first line, there's move EAX 7 here. We set EAX to 7. Move EAX EBX, set EAX to EBX. EBX is left unharmed though. Even though it's called move, EBX is still whatever it was before. And we're just going to ignore this last line for now. We'll come back to that later. 2 instructions that are pretty important are your comparison instructions. There's 2 main ways to compare values or check for equality. CMP or compare compares 2 values. It does subtraction under the hood, whereas test also compares 2 values and does a logical and under the hood. These are going to affect subsequent conditional jumps, and we're going to get into jumps in just a second. But basically, when you do a CMP EAX, your EAX 7, you're asking, is EAX minus 7 equal to 0? Or in a more human way, is EAX equal to 7? And same case with the test here. So that brings us into jumps. Jumps are kind of how you get around in assembly, or one of the main ways. And they do what they sound like. They perform a jump to another piece of code. So it's just going to skip over all the instructions in between. And in the case of JMP here, that's our unconditional jump instruction, which means that it's always taken, and just when it gets hit, it jumps to a new place in code. There are some other jump instructions like JE, JNE, JB, and JA. In order, those stand for jump equal, or jump if equal, jump not equal, jump below, and jump above. And these you can use after you do a comparison, and that will let you dictate where your code goes. And when I say you'll read that in the assembly. Odds are you're not writing assembly by hand, but the compiler will do this. So yeah, like I said, these are going to be taken depending on the result of the last comparator test. If the compare succeeded, it might jump, or it might just skip over it and keep going. And these can be affected by other instructions as well, but that's not really in the scope for today. This stack is super important. Or actually, before I get into the stack, are there any questions so far, or anything I can clarify? I know I'm moving through here fast, but there's a lot of content. I do also want to kind of walk through some of the demos, because some of this will make a little more sense once you can see it happening. Looks like no questions so far, so I'll get into the stack. The stack is a region in memory for short-term data storage. You can basically just think local variables. So if you're writing a function in C, any of the variables you define in that function are going to be stored in the stack. It's divided into segments called frames. So each function gets a stack frame, and a frame is basically the region on the stack that is relevant to that function. So like I said, when a function has local variables, those are all going to be contained within that function's stack frame. These frames are going to be bound by EBP and ESP. And from earlier, these are the stack base pointer and the stack pointer. EBP is going to point to the start of the stack frame, whereas ESP is going to point to the end of the stack frame. So that's kind of what I mean by they're bound. It's, the two extremes. And the stack is usually limited to about a megabyte of data. If you want to store more than that, you have the heap, which you've probably heard about in one of your programming classes. That's kind of outside the scope for today. One thing to know is the stack grows from high addresses to low addresses. I'm going to show some diagrams on the next slide, which grow from bottom to top, but the addresses will be indicated so you see which direction. So here is a function in C to calculate the perimeter of a rectangle. So you give it a length and a width, and it will give you the perimeter. So what might this look like on the stack? We have two local variables in the function here, total length and total width. And if we look at our stack here, we have EBP, and then right above EBP, we have our total length variable at EBP minus 4. Remember, this is 32-bit or x86 32-bit, so these are all going to be 4 bytes each as integers. So we have total length here, and then right above that, we have total width. Those are our two local variables. You'll notice, once again, the stack grows down in size. So we have 19FF80 here. We're getting the smaller addresses from higher to low. And then ESP and EBP point to our relevant bits on the stack here. So EBP points to our base, and ESP is always going to point to the top of the stack, or the end of the stack, which is going to be the most recently allocated local variable, or the one that's allocated last. We also have some arguments being passed to this function. We have a length and a width argument. these arguments are also going to be passed on the stack. You'll notice that the local variables from last slide are all going to be at EBP minus something, EBP minus an offset. Our arguments are going to be EBP plus an offset. So our length and width are going to be at EBP plus 8 and EBP plus 12, respectively. And that's the wrong slide. In between here, we have the EBP from the last function and the return address from the last function. We're going to cover that more later. I've kind of had these blanked out now to avoid getting into that, but also on the stack is going to be the EBP from the last function and the return address of where we were before, the address that we're going to return to afterwards. But I'll cover that more later if that's confusing now. But does anybody have any questions about the stack? All right. So when you're using the stack, there's two main instructions that you're going to be using, which are the push and the pop instruction. The push instruction is going to allow you to place a value on top of the stack, and the pop instruction will let you take a value off of the top of the stack. You can either just remove it or you can remove it and retrieve it, and we'll cover an example of that. The stack is what's considered a last in, first out data structure, which means that the last value that you pushed is going to be the first value that gets popped. And I'll kind of illustrate that now. So on the right here, we have some assembly, just a couple lines, and on the left, and on the right, I have an example of the stack. So right now, we're going to move 18 into EAX. Now EAX is equal to 18. And you'll notice I have the instruction pointer here to indicate where we're at. Now we're going to push EAX. Remember, the EAX is equal to 18. And as a result, now we have 18 on our stack here. We're going to move 99 into EAX, and then we're going to push EAX again. And now we have 99 on our stack. You'll see that it just keeps growing upwards in this diagram, downwards in memory. I know it's a little confusing, but it's easier to visualize this way. So one more time, we're going to put 42 into EAX, and then we're going to push EAX onto the stack again. And now we have a stack with all the numbers that we just pushed onto it. And you'll notice it's in reverse order of what we have here. We executed these downwards, and we keep adding values on top every time we do a push. Now we're going to go in the opposite direction. When you use the pop instruction, you can do just pop on its own, and that will remove a value from the top. We also can do pop EAX or another register, so we can retrieve the value on top of the stack and put it into a register. The reason I've done that is because you can see how these get affected as we go through here. So right now, 42 is our top value on the stack, and we know that that's for ESP points. When we do a pop EAX, 42 gets removed from the stack, and now 42 is in EAX. If we do a pop EBX now, we had 99 on our stack back here. We do our pop EBX, and that value gets taken off the stack, and now it's stored in EBX. One more time, our last value on the stack is 18. We're going to pop that. It's going to end up in ECX, and now our stack is empty. This bit here gets a little confusing, but in practice, when a compiler generates code, it usually doesn't generate a bunch of push pop instructions. And this also kind of covers what was going on earlier with that return address and the EBP, or the saved EBP. So at the beginning of a function, what we're going to do is we're going to do push EBP. What's happening is, remember that the stack is divided into frames, and each function gets a stack frame. So at the time that the function starts, EBP is still the EBP from the previous function. We're going to push EBP onto the stack so we can save that. Next, we're going to set EBP equal to ESP, which is the top of the stack. And then we're going to subtract a certain amount of bytes or a certain number from ESP. Figuratively, what this looks like is EBP and ESP both start here, and then we're subtracting from ESP to open up some room on the stack, is basically what we're doing. We're saying here's the space that all of our local variables are going to go. Then we have our function carry out. And then at the end of that function, we are going to move EBP back into ESP, or sorry, set ESP to be EBP. So we're going to shrink that space back down. And then we're going to pop EBP. And that basically, we're taking the EBP we saved at the beginning here, and we're setting EBP back to that. And then we're calling return, which is going to put us back at the function we started at. If this is confusing now, I would say don't worry about it too much. Most of the stuff we're going to be doing today doesn't require you to understand this. If you want to get into stuff like binary exploitation, this will be more relevant to understand, well, for sure. So a couple more different types of instructions. We have call, which is used to execute a subroutine. And basically what it does is it puts EIP onto the stack with a push and then jumps to the subroutine. So it's just a fancy way of jumping to a place, jumping to another section of the program, but also pushing EIP onto the stack at the same time. Return is kind of the opposite of call. It's going to take that old EIP on the stack off of the stack and then jump back there. Basically what this is doing is call is saying, let's save our spot in memory where we are now, push it onto the stack, jump to our next function, and then return just gets that saved spot back and goes back there. It's a way of going to and from. Get into a little more assembly syntax. It doesn't get too much worse after this. This is, close to the extent of what you need to know. Square brackets in assembly are essentially the dereference operator, or they are the dereference operator, similar to the star operator in C. In this instance here, let's assume that EBX is a pointer. And what we're doing with this move EAX and then EBX in brackets is we're taking the value pointed to by EBX and putting it into EAX. In C, this basically just looks like EAX equals star EBX. You're going to see the dereference operator a lot when you're working with the stack. EBP is going to be, remember, it's a pointer to the base of the current stack frame. Whenever you're referencing variables on the stack, you're always kind of just going to address them as EBP and then an offset. You're doing pointer arithmetic, essentially. So this move EAX brackets EBP minus hex C is equivalent to this in C. You're just taking that EBP minus hex C, wherever that is in memory, get what's pointed to by that. Another important thing that you might see is in yellow here, so this is a size directive. What this does is you have to remember that pointers point to a place in memory, but there's no, the size of what they point to is not conveyed at all. All the pointer is an address. So what this does is when you do move EAX, EBX without this yellow bit here, that's going to read whatever's pointed to at EBX into EAX, which I believe by default is going to be 32 bits there because EAX is 32 bits. Someone please correct me if I'm wrong about that. But when you do this byte pointer, what it does is it's going to read whatever's pointed to by EBX, but it's only going to read the first byte. This is particularly useful if you're working with strings, for example. You want to get the first character of a string. Well, you want the byte pointed to by EBX or whatever your string address is. And And there's all, there you'll see other ones. You'll see D word, word. It's just saying how much memory to read from that address, since that's not conveyed by the pointer, essentially. That's unknown. There's no way of knowing what it points or how big what it points to is. Another instruction that you'll see and is usually kind of confusing at first is LEA. LEA gets the address of something, is the best way to put it. In this instance, LEA, EAX, we have brackets here. You can kind of ignore them when you're working with LEA, but what you're saying is EBX plus 8, whatever the address of that is, put that into EAX. You'll see this used a lot when you're kind of doing some sort of pointer arithmetic. You'll take a pointer, add an offset to it, and then you want that address. So in this instance, EBX is a pointer. We want whatever is pointed to, and then 8 bytes after that, and then move it into EAX. So here's kind of a better example, hopefully. On our left here, we have our registers. EAX is just all zeroed out. EBX is 19FF74. On our right, we have our memory. We have 19FF74 here, and then we're growing upwards. And we have a bunch of different values. When we do LEA, EAX, EBX plus 8, let's think about what that's doing. EBX is 19FF74. If we add 8 to that, we add 4, we get here, we add another 4, we get here. Now we're at 19FF7C. EAX is going to be equal to 19FF7C. We did our arithmetic, EBX plus 8, we got here, and that's what we wanted. We wanted the address. On the other hand, we're going to do the same exact thing, but replace LEA with move. Now what's going to happen is we're going to get our EBX, we're going to add 8 to it, we're going to get up here, but now we want the value that's pointed to by that, which is going to be this 2B, 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 2B. So this isn't much different from the last slide, but after these two lines execute, what's going to be in EAX and what's going to be in ECX? So I'll give you guys a couple moments to write your answers. All right, so yeah, Kevin and Claire were both correct. In this instance, not in the right application. In this instance, EAX is going to be the 19FF7C, and ECX is going to be hex B5 all the way through. To review why that is, again, remember that LEA is getting the address, essentially what the result of this operation is. EBX is 19FF74. We're going to add 8 to that and get 19FF7C. Remember, these are in hexadecimal. And then that's why EAX is that, because LEA is going to give us the address. Move, on the other hand, remember we're using the square brackets to dereference here. We're taking EBX, we're adding 8, and then we're interested in what that points to, which are going to be these B5s all the way through. So another quick exercise. What's the final value of EAX after this? These are all instructions I covered, except for, I think, DEC down here. DEC is the opposite of INC. It just decrements a register by 1. LEA is just an add and a move at the same time. Kind of, yeah. Basically, LEA, you're going to give it a, a pointer, then an offset, and it's going to calculate what that is and then put it in the register that you told it. So I guess that's a good way to think about it. There's probably on a lower level, more differences than that, but I think that's probably a good way to think about it for today. If somebody else knows more about that, please write it in the chat. But I'll go back to the exercise here for the people who were working on that. So yeah, Owen raises a good point that it doesn't have to be a valid address. LEA will still do the arithmetic and give you whatever the answer was. And Adam is correct about the result of this operation here. So actually, I forgot to include it at the bottom, but the final value is going to be 49 because we're going to set EAX equal to 10. We're going to add 15. So now EAX is 25. We're going to multiply EAX by 2. So EAX is 50. And then we're going to decrement it. So we're at 49. The good news is that the hard part of this is essentially over. I'm going to dive into tools and then go over some examples. So disassemblers are one of the main tools you're going to be using for doing what's called static analysis, which is where you're analyzing software and without running it. You're opening it up and you're reading the assembly. This is a screenshot of IDA here, which is a popular tool I'll cover in a moment. And yeah, they're going to take your compiled executable, take that machine code, turn it into assembly so you can read it. And you get some nice stuff like this graph view where you can colorize different nodes and it will show you how the control flow works. And you can go through and read the assembly and try to figure out what's going on. So out of those disassemblers, IDA is a pretty popular one. It's kind of the industry standard, very mature product that's been around forever. Has arguably the best pseudocode generation, which I'll talk about in a second. Incredibly expensive. Binary Ninja is a modern alternative to IDA. Really good API, much less expensive. So if you're looking, to get into this, that's a better option than IDA. But if you're just looking to get started, the best option is definitely Ghidra, which is originally an internal NSA tool, but I think a year or two ago, it was made public and made free and open source. Very capable tool. And that's what we're going to be using today for our demos. Yes, and Binja is made by the founder of UFSIT, I believe. So that's pretty cool. Our other main tool we're going to use is debuggers, which you analyze software as it runs with a debugger. So if you remember from the examples that I showed earlier where I stepped through the stack, where I kind of did like the instruction by instruction, what happens, you can do that yourself with a debugger, basically with a real program. And you can manipulate data and control flow at runtime and, really kind of manipulate things and see what's going on and go through one instruction at a time to try to understand what's happening. GDB is like the standard most popular debugger for Linux, and some of the other Unices has lots of great third-party add-ons. WinDebug is the official Microsoft debugger for Windows. It's the only debugger that can debug the kernel. So if you're interested in that, you don't have a choice really. But for Windows, there's also x64 debug, which is a third-party open source debugger for Windows. Little more user-friendly. WinDebug, you're going to be doing a lot of commands and stuff. x64 debug is kind of a more point-and-click debugger, which makes it easier to get started with. There's also decompilers, which you should take that name with a grain of salt. It's very misleading. It's often not an actual decompiler. So both IDA and Ghidra include decompilers, which attempt to derive pseudocode from assembly, but that's not really a thing that you can do in compiled languages where you're compiling source code into machine code. You can't reverse that process. So these decompilers are basically just making educated guesses using different types of heuristics and whatnot to try to come up with what the equivalent C code for some assembly might look like. It's useful for getting an idea of what's going on, but they often, get stuff wrong, and sometimes it decompiles really cleanly, sometimes it doesn't. So you can't always rely on them, but they'll help you get a better idea of what's going on, at least at a first glance. There are real compilers for Java, or decompilers for Java and .NET. Those languages you can sometimes actually get the original source code. That's not really what we're talking about today, but you're welcome to look that up, on your own. Python isn't really explicitly a reverse engineering tool, but a lot of the libraries and other tools that you might use when you're reverse engineering are written in Python. So it's good to know, and it's pretty helpful for solving little problems or writing quick scripts to do things, which we'll show shortly. And then the last one will be hex editors, which just let you view a file as plain bytes. And there's some, you can analyze file formats, or you can try to patch programs with them. There's all sorts of stuff you can do. There's 010 editor is $50, pretty good. That one's kind of cool for analyzing file formats because it will show you the structure of that file and highlight stuff. HXD is a good free one for Windows. I don't believe it's available for Mac. If you're on Mac, I don't have it listed here, but I think there's one called HexFiend that's good. But now I guess we'll get into some demos. Scott raises a good point. Binja also doubles as a hex editor, which is pretty cool. So if I'm gonna make this full screen, if I know how. Vim has XSD mode. Yeah, there's a lot more options for hex editors. You can kind of hex edit in a bunch of different tools. There's actually a tool called XXD on Linux, which will give you a hex dump. But is this font size readable, or should I try to make this larger? Control plus doesn't make it larger. Is that better? No, it might always go all the way. All right. So if you have already downloaded Ghidra, you might have already found out that it's kind of weird that it's just like a folder you download, you extract it somewhere, and then it contains a file. If you're on Windows, it's called Ghidra run bat, or if you're on like Linux or Mac, it's just Ghidra run. But go ahead and do, if you're following along, do a quick Ghidra run, and that should open up Ghidra, and hopefully this works. So far, looking pretty good. If you've never opened Ghidra before, you'll have to create a new project, and I would just hit non-shared. I always call it a demo, and finish. I actually have to upload. I knew I was forgetting something. I have to upload these demo executables to the Discord. I'm trying to get out of full screen now. Give me just a second. I'm just going to throw these in the Discord real quick, just in case anyone wants to follow along. I will put them in the UFSit channel. Those are the executables we'll be going over today, and I'll upload these afterwards, like on my GitHub, so you can compile them yourself if you want. But I'm going to get back to the demo. So I have some little executables that I made to kind of do a gentle introduction here. We're going to do the easy pass one first. If we go in here, we run easy pass. It just says enter the secret password. So we'll guess password, and that was not the correct password, unfortunately. So let's see if we can open that up in Ghidra and get a better idea of what's going on. It should just show this, which it's asking you how you want to import it. You say okay. It'll take a sec. And it will open up. There we go. It'll say easy pass has not been analyzed. You're just going to hit yes. This should happen almost instantly. It's a very small executable. So now if you go in the sidebar here, this might look a little daunting at first, but just look in the sidebar here under the functions folder. You should see main in here. If you type in the filters and search for main, you'll also see it there. So this is our program, but in assembly. And this was produced by the compiler. And on the right here, we have the decompiler, which I was talking about earlier. This is Ghidra's best guess of what this function might look like if it was written in C. So if we look at the assembly here, you might recognize this if you remember the function prologue thing I talked about. We'll see we do an LEA to get this enter the secret password string. I'm not going to go in depth on how all of this is working, but the point of interest is if you're familiar with C programming, a couple of things should stick out. There's a call to printf, and actually this font might be too small too. Are you guys able to see this? I don't even know where font it is in Ghidra. Is this visible or no? Listing fields. If anybody knows where font size is in Ghidra, I would appreciate that information. But hopefully it's visible enough. But you might see this call printf here, and you might see this call fgets, and you might see strn compare. Tools, options, listing, display. I was so close. I appreciate that so much. That is so much better. Okay. I was a little fiddly trying to resize. I was making full screen. Now you should be able to see this like a lot better. The decompilation is still a little small, but oh well. So you should notice there's an fgets, string compare, another printf. You might have already seen this here, but if we look at this string compare, we can see above here, there's this one was easy string, and that's being used in our string compare. So this one doesn't require a whole lot of actual reverse engineering. You could have actually, there's another tool on Linux called strings that you can run. And, you know, if you look through here, you might have found that eventually you see enter the secret password, and then this one was easy. This one didn't require a lot of reverse engineering, but, you know, we opened it up in Ghidra. We saw that this string was being used with this string compare, and that's probably a pretty good guess for what the password might be. So if we try this again, and it asks for the secret password, and I paste that in, it turns out that is the correct password. So I'll open up, if anyone has any questions about this, I would say ask now, but I'm also going to open up a slightly harder one. I'll save that. I think we're going to try the medium one, if I remember what this one is. Once again, we're just going to open it up, analyze, and go to the main function. I'd love to give a more comprehensive guide on how to use Ghidra, but I guess I'm trying to talk about the reverse engineering part right now. There's a lot of different things to cover, but this time we see our same call to printf in the beginning, and we see that string above the enter the secret password. So we kind of know what's going on here. And the decompiler can confirm that. There's another fgets, which is where we're going to get our input if you're familiar with C programming. But now we're loading this weird string here, 6ff. It doesn't look significant, but we can try using that as the password. So this one was the medium pass. We enter this. That's not the right password. So our strategy of just looking for something that looks like the password and trying it isn't going to work this time. So we're going to have to look a little more carefully here. If we use the decompiler a little bit, just for the sake of speeding this up, and hopefully this font is large enough, but we're doing a string compare with local 28. Yeah, that's what, decompiler display. Okay. This font. Listing display. Yeah, I don't know where it is.
You were just there in display. Yeah. Then font. Down a bit.
I can't read. I'm sorry. There we go. Thank you. You can see that I don't spend most of my time in Ghidra, but so now let's look at this code here. We have this string compare with this local 28 variable and this string here. I'm just going to rename this to input because we can presume that's what it is based off running the program. It's always a good idea to run the program first so you can, kind of know what to look for. And right above here, we do this, we're doing some stuff to input. We're doing a while loop with something about the length of input. So to me, that sounds like we're iterating over input and we're doing something to it. And then this looks like a counter. This is the length of theirs. This looks like the length of our string. We're calling strlen on input. So this is probably input length. And like, once again, if you hit L, you can rename variables. And then if input length is less than local 30, break, and we're doing input local 30 equals input local 30 plus hex 2, and then we're incrementing local 30. So this sounds like a for loop that we stumbled upon. Ghidra doesn't support those yet, but we can just call this like I or something, like it's a for loop. And while this doesn't look ideal, essentially what's going on here is we're going through this string, and for every character, we're adding 2 to it. And then we're checking if it's equal to this string here. So we need to put something in that once you add 2 to each of the characters, it turns into this string. Well, the easiest way to find out what that might be is to just do that in reverse. If I open up Python, I will let, password or pass equal this. Find my Python again. Pass equals that string we found in the binary. I think pass is a keyword. That's cool. And then do a quick for C in password. I'll create flag equals just an empty string, and then for C in password. We're going to do flag equal or plus equals CHR forward C minus 2. This is just kind of how, because of the thing how Python works. If it was C, you wouldn't have to do this, but we're saying get the integer value of that character, subtract 2, and then get the character value. And I think if I do that and then print flag right here, it says add 2 to each byte. And that's what we had here. So this is kind of like our decrypted answer. If I quit out of here and then run that again and paste in our add 2 to each byte, that's the correct password. So after reverse engineering this, we found out that it's adding 2 to each of our bytes and then comparing it to this because it's trying to hide the password. There's one scenario, and this will be the last demo, where this might not work. And I'll show you what that scenario is. So I'm going to close out this one here. I'm going to open up the sacred number demo. And before we start that, I'll run the sacred number demo. How come the closing back in the password wasn't part of flag? I might have accidentally copied an extra thing. That's a great question. That is an unfair advantage since I wrote the demo that I knew that wasn't part of the flag, but I think I might have mistyped something somewhere, and that's why that ended up in the output. I'm sure it was a simple mistake. So we're going to run the sacred number demo, and it's asking for what the sacred number is, and we're going to guess that it's 100. That wasn't the sacred number, so we're going to have to reverse engineer it. If we open this up, we're going to analyze it and then go find our main function. And as soon as we get into main, yeah, Scott's answer is correct. If we do call, right into our main, we do call get sacred number. So that sounds kind of like what we're looking for. And if we go in here though, this is kind of suspect. There's a lot going on here. Even normally we can lean on the decompiler to help us, but this is getting a random value and then it's doing a bunch of crazy math. This is, we can't really reverse, especially because it's a random value, but we can't really reverse engineer this, just by looking at it. So this is a great time to use a debugger. We're on Linux, so we're going to use GDB. And we're just going to open up the sacred number executable. Excuse me. And we're going to do in GDB. I'm using something called Jeff that's already installed. These commands should be pretty much the same for you, but it will show things in a way that's easier for me to present. So in GDB, if I do disass main, disass is short for disassembly. This is the disassembly of our main function, and this will look very similar to what we have in Ghidra. Quickly looking through here, we'll see some functions of interest. There's the get sacred number, there's a printf, there's a call scanf, and then right after that scanf, we do a compare. So it sounds like that's probably a good place to start. So what I'll do is I will set a breakpoint at this line here. GDB is a whole different beast of its own, so I can't explain all of it right now, but what you can do is you can do B for breakpoint star main plus 69, and that's because this is our main function, and then at the offset of 69 is where we're doing our comparison. If you remember earlier, comparison is used to compare two numbers. And then right after we have a JNE for jump not equal. So depending on what happens here, we're either going to get the you found the number message or the you didn't find the number message. So we're going to set a breakpoint. What that means is when we run the program and it gets to that point, the program is just going to halt right there. And then we can look around. So if I hit R, if I type in R to run, it's going to ask for the sacred number. And I'm going to guess 100 again. Maybe we'll get lucky. But now we just hit the breakpoint, and I'll try to make this window a little bigger. And now we have a printout of everything that's going on here. So we're at this line, compare eword x, compare ECX to dword pointer EBP minus 8. So that's going to be a variable on the stack, if we remember. And then if we look at ECX, we see that's hex 64. So that's actually the variable we just entered. 100, I think, is 64 in hex. That sounds about correct. So we're comparing that against EBP minus 8. Well, EBP is here. This is our little printout of the stack. EBP is here. We have our little indicator. And then minus 8 is this right here. Hex F5, 7, whatever. So if we just copy that, open up a new tab, 3, and then paste that value in. String cannot be interpreted. Oh, whoops. It's been a while. Just like that. There we go. That's the same value in decimal, which is what we're looking for. So if we copy this and then hit C to continue, that wasn't the sacred number because we, what's it called? We set our breakpoint after it was already found. So that was kind of my bad. But if we exit out of, or we quit out of GDB and open this up again, do disass main, we can see we did a call get sacred number right at the beginning, and that happens before we check. So maybe if we can intercept that, we can find out the number and then put it in. So I'm going to break right after this call at main plus 18. Run, and we hit our breakpoint. One thing that I didn't mention earlier, but is kind of in the follow-up part, is in x86, return values usually end up in EAX if you're returning a value from a function. So in this instance, EAX, we'll see, looks pretty similar to what we had before. This is another big number. So if I copy that, and then is that actually the exact same number? It's because I didn't seed the random generator. That's why. We have a big number now. And now, if we hit C to continue, it asks for the number. We use our debugger to find out what the number was. We can hit enter, and it says you've discovered the number correctly. So I realize these demos are a little bit difficult to follow, especially if you're new. But a lot of this is just going to be practice. This is my last demo. But a lot of this is just practice and learning how to use these tools. I wish I could have, gone deep into how to use Ghidra and GDB, but we would be here all day, unfortunately. So that's actually the last of my demos. So I'll exit out of here, come back here. So yeah, I'll leave you with an analogy, I guess, about reverse engineering. You can think about equating this to writing words on a piece of paper. Your program is like a paragraph. Your paragraph is your entire program. Sentences are functions. There's many functions in your program. Words are parts of a function. There's many words in a sentence. Letters are lines of code. Many letters in a word. Pen strokes are instructions. I'm kind of saying that to emphasize how primitive a lot of these operations are. Pen strokes, instructions are very simple. They do one thing, and when you're seeing a lot of them, it's difficult to understand. If I gave you a paragraph written out by hand and gave it to you, you could read it. But if I gave you the directions on how to make every pen stroke to then write that same paragraph, you would have a very hard time understanding what I'm saying. So reverse engineering is basically about turning pen strokes into paragraphs. When you open stuff up in Ghidra, it's, things might not be immediately apparent. And if you sit there and read every single instruction all day, you will have spent a lot of time. And then, you might not even find out what's going on. It's difficult to understand. the whole idea of this is seeing the bigger picture. So as you get better at this and you practice more, you will learn how to spot patterns, learn what's going on, and you'll be able to turn pen strokes into paragraphs figuratively. You'll be able to read a bunch of instructions and get an idea of what something's doing. So if you're interested in this, which hopefully you are, next up you could learn about 64-bit x86. So what I covered today is 32-bit, which odds are you're not watching this on a 32-bit computer. 64-bit x86 is very similar though. So you're already off to a great start. You'll learn about calling conventions, especially too, if you start looking at 64-bit. Recommend that you try some challenges and learn. A lot of these concepts today I had to go through kind of quickly. The stack, registers, all these different instructions. Learn how those work in detail. There are resources online where you can look up kind of how these work. Some additional resources you might want, and there's a typo on the third line. I'll fix that. But there's a really long book. It's like 1,200 pages called Reverse Engineering for Beginners, which sounds scary, but the beginning of it is pretty good. The whole book is pretty good, but that will cover things like this way more comprehensively than I covered them today. Compiler Explorer, which I'm actually going to demo in a moment because that one's really important, will show you how C translates into assembly. CrackMe's.1 has a bunch of reverse engineering exercises that you can download and then try. Similar to what I showed you today, where you have to find a password. Someone will make you discover a key generation algorithm. There's NSA reverse engineering resources. I'm going to publish these slides afterwards so you can click on all the links and whatnot. And then Live Overflow is a good channel on YouTube. I'll show Compiler Explorer. For anyone who's interested, I'll show Compiler Explorer. But that concludes my presentation. Thank you all for coming. I hope that you learned something, hopefully. If you have any questions about any of this stuff, feel free to DM me in Discord or ask anyone in Discord. And I can kind of give you a better explanation than I can give you here today, I guess. But if you have any questions, you want to learn what to explore next, or, you're doing a reverse engineering problem and you're stuck on something, you can always shoot me a message and I'll try to help out. So I hope you all enjoyed. I don't have anything else. I don't know if Claire wanted to say anything at the end of the meeting. I'll go over Compiler Explorer real quick for anyone who wants to stay, but that is the extent of the material I have for you. But I will quickly cover.
I don't have anything on my end, so
Explorer.
you can go ahead and take control still with Compiler. So I don't have anything on my end, so you can keep going for as long as you want, showing them Compiler Explorer and stuff like that.
Sounds good. Here, I'm gonna. For some reason, the one on my personal one is messed up, but so this is Compiler Explorer. If you are interested in reverse engineering, this is one of the best things I can recommend that you use, because what this does is it allows you to write code in C or many other languages on the left and see the assembly on the right. And you can choose from different compilers and whatnot. So this right here is an example of just a function that squares a number. It takes a number as an argument, and then it returns that times itself. And it does this color coding and everything. You'll see at the beginning of the function, it does this push EBP, move EBP ESP. That's the function prolog I was talking about earlier. Next, we're moving dword pointer EBP plus 8, which that's going to be our number argument in num here, into EAX. And then we're multiplying EAX by EAX, popping EBP and returning. What this does is it takes an argument, it moves it into EAX, doubles EAX, and then the return value is EAX. So it doesn't have to do anything else. This, I would highly recommend. I cannot recommend enough. If you are interested in learning more about reverse engineering, there are plenty of great exercises you can do online. There's no shortage of things to try to reverse engineer, but if you want to get an idea, so when you're reading assembly and you want to be able to see, what does this look like in C? What is this actually doing? This is something I cannot recommend enough, because this allows you to see, you know, with color coding line by line, what it looks like. And here, let's try our perimeter function from earlier. You know, if we do width and length, and then that will fail to compile because that's not a variable anymore. And we do, you know, total width equals width times 2, total this was our perimeter function from earlier that I did in the demo. And you'll see at the beginning, there is this push EBP, you know, allocates the space on the stack. That's that function prologue I was talking about. You'll see this almost all the time. Next, we're going to move D word pointer, or we're going to move the D word pointed to. Oh, that's definitely a good point. Claire raises a good point, is that almost every software does not want you to reverse engineer it. So, I mean, if you are doing that, do it on your own time. Maybe you shouldn't do anything that you're not permitted to reverse engineer. Definitely don't, you know, post that or tell the company about it, because that might not work out for you. But here, you know, this line we have in yellow, it's highlighted like that, but we have our total width variable, which we're storing in EAX. We are taking the D word pointed to by EBP plus 8, which is what we're doing here. Moving into EAX, we're adding EAX to itself, which is the same thing as doubling it. And then we're moving that into EBP minus 4. Remember that EBP minus 4 is one of our local variables, in this case, or the total width. Similar story with the total length, just with different variables. Then we're moving EDX, EBP minus 8, and putting EAX, or EBP minus 4 into EAX, adding the two, or adding EDX to EAX, and then we return that. So that's what our perimeter function looks like. And if you look at that diagram from earlier, you will see what the stack should look like for this. One thing to note, if you do play around with this, I was talking about x64 or x86 assembly. You might have to add this M32 flag here so that it outputs 32-bit, because it will output 64 by default. But that's pretty much all I have. I would encourage you all to play around with this, play around with some of the challenges on the websites that I linked. And if you have any other questions, there's some potential copyright issues. Yeah, definitely don't reverse engineer anything that you don't have permission to reverse engineer. You know, there are plenty of things on the internet, CTF challenges, crack me's, exactly. You can see RE and CTFs. You know, reverse engineer stuff that has been designed to reverse engineer. You should not reverse engineer anything that is, you know, prohibited to reverse engineer. So yeah, that's all I have for today, but I encourage you all to try this out on your own and ask me if you have any questions. I'm always interested in talking reverse engineering. So if you're interested in it and you want to get started, or you still don't know where to start, talk to me, and I'll try to help you out. So that's that. I don't have anything else to say. Thank you all for coming.
Thank you so much, John. We really appreciate you giving this presentation. It was very thorough and informative, so I'm sure everyone here appreciated it. If anyone has any questions, feel free to reach out to him over Discord, or if you have any questions right now, you can go ahead and ask.
Yeah, I'll take questions now. And also, I need to clean up these slides just a bit, fix a couple typos I found while I was presenting, and then I will upload these to the Discord so anyone who wants to go through them again can have them. And I'm thinking about I'll probably put everything on GitHub afterwards as well, just for anyone who's curious. So I'll notify you when that comes out. But if there's anyone who has questions now, just ask in chat or over voice. And if not, then we can all get going.